go ahead and get started. Pseudo Chapter 9. We're looking at the chemistry of aromatic structures. So when we go through and do these reactions, there's one mechanism that you're ultimately responsible for, and that is the electrophilic aromatic substitution mechanism. So let's go ahead and break the name down. When we're looking at the electrophilic, we're looking at something that is electron loving. So let's come up with a nice symbol, simple symbol to represent our electrophile. What can you tell me about the electrophile? I'm going to assume that's what you meant and not that I was the devil, but... So we can go with a positive charge. It's usually nice to put that positive charge on some kind of element or atom, but because we don't know what that atom is at this point, we're going to go generic and just give it an E. Okay? Next part, aromatic. We haven't talked about what aromatic structures are yet, but in general, particularly when we're looking at the EAS reaction, when we think aromatic, you need to be thinking of benzene. So a six-membered carbon ring with the double bonds. Aromatic is ultimately referring to extremely stable. There's lots of resonance when you look at the benzene ring. So those pi bonds can shift around, which we briefly talked about, 15 minutes ago. Okay? The last part is substitution. So substitution is eliciting that we are doing some kind of reaction. So we can add our reaction arrow, and if we're going to do the substitution, we now need to predict what we're substituting for what. Okay? So we've specified that our electrophile is atom E, so that's probably going to have to substitute for something within the benzene ring. So what somethings are in the benzene ring? Carbon and hydrogen. Of those two, which one is most likely to be substituted for? Why the hydrogen? It's easier to break off. Why? One bond versus the four bonds for breaking out an individual carbon. So if we did a substitution with the carbon, we'd have to break those four bonds, and then the electrophile would have to remake four bonds as well. Okay? So it makes sense that we're going to do a substitution for our hydrogen, so we could draw out our predicted product. We would have our benzene ring with the electrophile, and if we were going to balance it, we've got H+. Okay? So when we're looking at an EAS reaction, that is what's occurring. Okay? All put together in kind of a relatively simple step. Okay? So now what we're going to have to do is evaluate what happens. Whoops. Oh, cool. Mechanistically. So we'll look at each step of the reaction and try and evaluate what occurs. Okay? So when we take a look at our starting materials, is there anything that jumps out at you as particularly reactive? E+, our electrophile. What do we need to stabilize that positive charge? Electrons. Where do we have electrons? In the pi bonds. Okay. Why do we not go to the hydrogens? Not quite. There's still two electrons in a carbon-hydrogen bond. Why jump to the pi bonds, not the sigma bond? If we're comparing our reactivity, our aromatic ring is very, very similar to, say, an alkene. And when we look at the reactivity of an alkene, we're looking at our pi bond reacting. It's the pi electrons. Why were the pi electrons reactive? They're the highest energy bond. Okay, our sigma bonds have S character. They're a little bit lower in energy. Our pi bonds are the most reactive in this case. So what we're going to do is take those pi electrons and we're going to react them with our electrophile. Okay? So what's the result? What do we get from that? We didn't do anything to the sigma structure, so that's still there. I'm going to imply hydrogens except for one important one. Where does the electrophile bond? Which carbon? Either one. Just like with the alkene, if there isn't a difference between them, we'll just put it on there. At this stage, there's no difference, so we can just attach our electrophile to one of those carbons. We still have that hydrogen. Okay, we did not get rid of it. And we still technically have that hydrogen. Would this be a correct structure? What's missing? Charge. That carbon is positively charged. Okay? So after our first step of the reaction, we've shifted our positive charge from being on the electrophile to being on a carbon. Okay? Is this structure stable? No. What do we need to stabilize it? We need electrons. Okay? If we look for something negative, we're ultimately looking outside the structure, okay, and trying to bring electrons in to directly stabilize it, like a nucleophile. Okay? Except if we do that, okay, what ends up happening? Well, we lose the aromaticity of our structure. We no longer have the resonance. Okay? So that's ultimately going to be a bad thing. But, taking even a step further back, before we even look at a negative outside the structure, we should look for our highest energy electrons. Where are the highest energy electrons? In the pi bonds. So what we'll do is move the pi bonds first and see what happens. So what we'll do is pick one pi bond, go from bond to bond. What changes? Heard something about our charge. What happened to the charge? Our carbon that was positive is now neutral, but our other carbon is now positive. What's the relationship between these two structures? Resonance, we need to add that double-headed arrow. Okay? We still have that positive carbon, so we still want to try and stabilize it. Where are our highest energy electrons? Still in the pi bonds, so we'll shift that over. Now what happens? I'm going to swap this. Any objections to what I just did with the hydrogen and the electrophile? Okay, all we've done is just flip the structure over ultimately. So where the electrophile and hydrogen are irrelevant. Okay? We still don't have complete resonance. We cannot push resonance or push electrons through this blue carbon. Okay, why not? What's that? No, it's not a bad idea, or at least not directly. It already has its 4 bonds. We can't push a pi bond through it that's putting too many electrons around that carbon. Okay? So we've lost resonance around the whole ring. These structures carry a very particular name, and it's all based on that blue carbon. What can you tell me about the bonds around that blue carbon? Wow, I think I actually heard someone say it. They are all sigma bonds. These 3 structures typically get called sigma complexes or sigma structures. Okay? They're incredibly important as far as evaluating your products. Okay? So if we level up the difficulty of the problem, which we will in just a little bit, you need to evaluate these 3 resonance structures with the new changes to it. Okay? It still doesn't get us to our final result. Okay, so let's go ahead and draw what our final result is, because we already predicted what it was going to be. What did we say our result was going to be? With our E and H plus needs to be coming off. Okay, and draw on my pi bonds. So what changed? What do I have to do mechanistically? What's that? How do I remove that hydrogen? Got the right idea. I want to take the electrons in that bond and I want to put them into the pi system. Okay? That new bond came from our hydrogen, that pi bond. Okay? How could we facilitate that bond breaking? We could add a base if you... Oh, why did it do that? Okay, we have an electrophile here, and we have our nucleophile in our benzene ring. And when we started this whole mechanism off, we looked at our electrophile first. We said that was positively charged, that's why it would react. What would happen to the reaction if I got rid of that positive charge? Would we expect it to go faster or slower? Slower, because it's no longer positive. It's no longer as good of an electrophile. Okay? So what could I do to make it go faster? I could make the electrophile more positive. What else could I try and do? Instead of attacking the electrophile, I could go through, I could change the nucleophile. What do I need to change to the nucleophile? It needs to become more negative. Okay? So when we're looking at individual reactions and catalysis, ultimately those are the two things we're targeting. Either making the nucleophile more nucleophilic, i.e. making it more negative, or making our electrophile more positive, okay, or more electrophilic. Okay? So what we're going to do is look real quickly, okay, at how we can speed the reaction. So this is evaluating our electrophile. We can make our electrophile more electrophilic by making it more positive. So if we take a look at these three possible structures, which of those three is the most electrophilic? To be an electrophile, what does it need to be? Which of those three is the most positive? Probably the one with the positive charge. That sounds pretty reasonable. I like that guess. Okay. So that one's going to be our most electrophilic. How about between the other two? Okay, why do you say the carbon will be more electrophilic than our bromines? The carbon is bound to electronegative elements, meaning that that carbon becomes more positive. Okay? So to speed the reaction, we can go through and add different catalysts. Okay? We'll talk about these more in lecture, so I'm not going to spend too much time on them here. But what we can do in the case of the bromine is we can add iron tribromide. What can you tell me about the iron atom in iron tribromide? Is it positive or negative? It's pretty positive. Okay? What can we do to stabilize that positive? We need to give it some more electrons. Do we have electrons nearby? The bromine can share its electrons. But then how many bonds does that terminal bromine have? It's too many bonds. So we need to break a bond. How are we going to break this bond? Where do those electrons go? Left or right? Our bromine donated electrons, so it starts to become what charge? Positive. How do we stabilize that positive? It needs more electrons. So we'll take the electrons in that bond and shift them towards the bromine. What happens to our last bromine? That last bromine has now lost electrons. It is now formally positive. What did we do? Just made the electrophile more electrophilic by adding this catalyst. We made a bromonium cation. Okay? So that's how our catalyst works to speed the reaction for our bromine electrophile. How about on the other end? We can go through and do something similar. Except instead of iron tribromide, we're going to use aluminum trichloride. What's special about aluminum? Having a periodic table is helpful. It's a metal. It also has sp2 hybridization, which means what is left over? An empty 2p orbital. What can we put in an empty p orbital? We can take the electrons from our chlorine and donate them in. The problem with that is now chlorine has too many bonds. So what do we do with the electrons? Chlorine's then going to take those as well. What's the result? I like talking about this one, which we'll talk about here in a second. We generate a positively charged carbon. Our electrophile is now more electrophilic. This has, while it looks pretty wickedly unstable, it has a resonance structure where the oxygen can share its electrons. Okay. This species is kind of fun. In fact, some people might even say it's a little silly because it's the acylium ion. You're not going to be able to stop laughing. You can go home and tell everybody that joke. It's awesome. Okay, so what we end up doing in each of these cases is increasing the electrophilicity of our electrophile by tweaking its chemistry, by taking the electrons away from it. Okay? So, what happens if we want to try to tweak our nucleophile? Okay, so in this case, our aromatic ring acts as the nucleophile. So we'll add that little note here so we don't forget it. Okay, to act as a nucleophile, our ring needs more electrons. Okay, so let's look at, say, our central benzene, because that's where it's starting. How do I put more electrons into that structure? So I want to add a catalyst that puts more electrons in. Where do we put those electrons? Okay, well, we can break the bonds, but how does that put electrons into the structure? Where would we put those electrons? What atom in benzene can accept more electrons? So if we break something off of it, we can put more electrons in. But the structure itself cannot accept more electrons, which means we can't add a catalyst. Okay? So what we're going to have to do is physically alter the structure, which is what you guys were getting at. Break something off, put on a new group. Okay? So what we're looking at in each of these cases is comparing atom X always back to hydrogen. Okay, so we've got two new cases that we need to evaluate. So we'll start at the top. What can you tell me about atom X? In particular, in comparison to hydrogen. Okay, we're going to make that a little bit more generic. Instead of saying lone pairs, we're going to say atom X has more electrons than hydrogen. Okay, and not just a hydrogen, but a hydrogen atom. Okay, how could we see more electrons? You guys already came up with one. A lone pair. Could see negative charge. Okay, and we'll look at a couple examples of other things that aren't quite as obvious. Okay, how does that affect our reaction? Okay, so now if we were going to look at our substitution reaction, we need to substitute for a hydrogen. When we looked at benzene, did it matter which hydrogen we substituted for? No, why not? They're all the same. When we look at this new structure, are all those hydrogens the same? If I take a look at this hydrogen, and it looks that way, it sees atom X, and this way it sees hydrogen, right? What if I take a look at this hydrogen? What does it see?
The same hydrogen.
It sees hydrogen and hydrogen. Are all of these hydrogens the same? No. What we end up finding out is that we get 3 different types of hydrogens. Okay? So what we're going to do is tweak it on our benzene structure. We can number out these hydrogens. Okay, we could call these positions 2, 3, 4, 5, and 6. Why would I start numbering that way? Because X is by definition an atom 1 on a ring. Okay? So I could say position 2 and 6 are ultimately the same, and 3 and 5 are the same. Okay? So that's helpful, except as you've seen whenever I add things, chemists aren't the best at mathematics. Okay? So we like to think that we can speak better than we can add. So instead of using numbers, we come up with words. So the 2 and 6 positions get a new name. Okay, so let's come up with a nice name that makes sense for 2 and 6. So I think, ortho sounds just like 2 and 6. So there we go. There's our ortho positions, are 2 and 6. I didn't come up with this, so don't blame me. How about 3 and 5? Well, 3 and 5 sounds an awful lot like Did you really just say meta? Oh, okay. We've got the meta positions. And then position 4, all on its own, we have para. Okay? Of course, chemists really aren't as good as we think at using words. So what do we end up changing that even further down to? We'll go to symbols, okay, or a single letter. We'll use P for para, Z for meta. I was just kidding, just seeing if you were paying attention. We get M for meta, and we get O for ortho. So 3 different ways we can refer to those positions, either by number, by word, or by letter. Okay, which is going to become relevant here. Undo. There is no undo. Well, this is why you take notes again, because your instructor's a klutz. So, our top case. We said atom X has more electrons than hydrogen. Okay? So what happens? We want to see how that affects the ring, which means what do we need to look at? Everybody's favorite 9-letter word? Resonance. So we're going to take the electrons on that oxygen and we're going to move them towards the ring, because our oxygen is going to act as a source of electrons. How many bonds would our carbon then have at the top? So what do? We break the pi bond. What charge builds on that carbon then? Gained electrons, we now have a negative charge. You can continue to draw resonance structures, which I'm going to draw as kind of pseudo blanks here. Okay, and I'll leave you to make sure you put in the double bonds in the right spots. Okay, and we can put a negative charge here. Okay, so we've done what to the ring? What does it become? Not stabilized. If it's negatively charged, that's not a stable thing. What were we trying to do? We were trying to make the aromatic ring more nucleophilic. What's a characteristic signal for a nucleophile? Negative charge. So if atom X added to a ring, so that first atom has more electrons than a hydrogen, that atom X can donate electrons into the ring and put negative charge at our, let me make sure we get the numbers right, 2, 6, and 4 positions, or our ortho and para positions. What does that do to the reactivity of this benzene ring? Does it react faster or slower? It should react faster. Being these pseudo, I guess it's not really pseudo, geeks that we are, like to come up with some fancy name to apply to this, we end up calling atom X an activator. Okay? And if we were going to do the substitution reaction, we would predict that the electrophile is going to do a substitution for a hydrogen located at what positions? I think I heard you say it. Our para and ortho positions. Why? That's where the negative charge is. Okay? Makes sense? Okay. What happens if we now move to the bottom case? What can you tell me about atom X now? Okay, go following the same pattern that we had before. X has less electrons. Okay, so there are some cases where atom X will have less electrons than a hydrogen atom. How do we get less electrons than a hydrogen atom? How many electrons does a hydrogen atom have? What happens if we get rid of one electron? What would we see? What is that? We would see a positive charge. So if we can somehow put a positive charge on atom X, we're looking at a new classification. How does this affect our reaction? Well, atom X is positive, so how do we neutralize it? We give it electrons. Where do we have electrons? Pi bond in the ring. What's the result? We put a positive charge on the ring. If we continue, you should notice that you should be able to put positive charge at our ortho and para positions. Again, fix the double bonds. What is this going to do to the speed of the reaction? The reaction should slow down because we've put a positive charge on the ring. Our ring needs to act as a nucleophile, which means it needs to be negative. Okay? So what is the result? We get atom X being a deactivator. Where's our reaction going to occur? Where would we expect our substitution? Substitution needs to occur where there are electrons. Our ortho and para positions absolutely have charge, but what charge do they have? Positive charge. Our ring must act as a nucleophile. All we're left with is the meta position being the reacting position. Okay? So let's look at a couple examples here, see what you guys can come up with. Activator or deactivator? Feel free to shout it out, you know. What's atom X in that first structure? What's atom X? What is the atom itself? Oxygen. Does oxygen have more or less electrons than hydrogen? It has more, which means it's an activator. We would expect our substitution to occur at which position? We would expect our ortho or para position. How about the next one? What's the atom? Carbon. Does carbon have more electrons or less electrons than hydrogen? More, which means activator. Next one. What's atom X? Nitrogen. Does nitrogen have more electrons or less electrons than hydrogen?
Less.
Why do you say less? I think I know why you're saying, yeah, less. Because of the formal positive. Nitrogen typically would have more electrons, but because the nitrogen is formally positive, it has less electrons than hydrogen. Okay? There is a negative charge on that oxygen. Irrelevant. That's not atom X. Atom X must be immediately bound to the ring. Okay? So in this case, what would we expect? Activator or deactivator?
Yeah.
We get a deactivator. Go through and put letters. Whoops, that was supposed to be a D. And the last one. What's atom X? It's a carbon. Activator, deactivator. Why do you say deactivator? In our second case, it was carbon, and that was an activator. You're right. Why is it partially positive? The oxygens next to it withdraw electron density away from that carbon. That carbon ends up picking up a partial positive charge. How do you know it's partially positive? You draw out a resonance structure where you see the formal positive. You have a deactivator with that group. Okay? Makes sense? Kind of get the idea of it. This little chart thing that I just drew out here answers 90% of EAS chemistry. Okay? It answers pretty much all of the questions that the post-lab asks. Okay? You just have to classify what atom X is and shuttle it into the correct categories. The one exception, because I'm pretty sure they ask it to you, is chlorobenzene on the list?
Yeah.
The one exception is going to be if atom X is a halogen. Okay, so let's real quickly take a look at that example, and then we're almost done, I promise. Let's draw chlorine. What is atom X? Chlorine. Does chlorine have more electrons or less electrons than hydrogen? More, which would mean we would expect chlorine to act as an activator and donate electrons into the ring. Yes? Why are you shaking your head? Why does it not want to donate? Chlorine is electronegative. Chlorine would rather take electrons. So our halogens hit this really weird gray area. They have the extra electrons to mean they could activate, but they're electron withdrawing groups because of their electronegativity. So what does that end up meaning? What we get for our halogens, so this could be bromine, chlorine, iodine, fluorine. If we have a halogen, we have a deactivating group because of their electron withdrawing effect, their electronegativity. But when we go to substitute, we get the para-ortho directing. Okay? So they pick a little bit out of each of those two categories. You now have all of the chemistry that you can see with EAS reactions as far as substitution patterns go. Okay? Questions about that? That was not a small amount of material. That's a lot of stuff to process. Okay? Last part of this that we need to discuss would be what you're actually doing. Oops. You're going to go through and nitrate, I believe it's ethylbenzoate. Okay, so for this reaction to work, your electrophile is going to be the nitronium ion. So NO2 plus. And we're going to react this. Is it ethylbenzoate? Methyl? Is that what you were saying earlier? Sorry. Okay. And we're going to do the nitration reaction. Okay. With these two species, you will answer the last question, which is a mechanism. So at the very beginning, when we drew out the EAS mechanism, I drew it out generically. You now need to go through and change the electrophile to the nitronium ion, and you need to change the nucleophile to methylbenzoate. Okay? And draw in each of those individual steps. Okay? Going into this experiment, we now have the resources to be able to predict where we would expect the nitro to substitute. What should our product be? Where should the nitro go? To the ortho, the meta, or the para? Which reminds me, why is the para off to the side right now as opposed to immediately below? Ortho, meta, and para are all relative to some position. Okay? It's not up and down, it's relative to whatever group you're looking at. In this case, I drew the group to the side just because it was easier for me to draw it there. Okay? Para is always directly opposite that. Ortho is always the closest group. Meta is the one in between. Okay? Where would we expect our nitro to go? Okay. What's atom X? Carbon. Does that carbon have more electrons or less electrons than hydrogen?
More.
If it has more, then we wouldn't be able to draw, say, a resonance structure that looks something like this. Is this a valid resonance structure? Where what we did was took the electrons in that pi bond and gave them to oxygen, being a more electronegative element than carbon. What charge did we just put on that carbon? Positive. Does that positive carbon have more electrons or less electrons than hydrogen? Less, which means where does the nitro go? The meta position. So we would expect our product to be the meta nitro ethylbenzoate. Okay? Questions about that? Okay, very, very, very last slide, I promise. Oh, crap.
Sorry. Well, so you had the two double bonds to the NO2.
Yeah.
And then it bonded to that carbon. So
Yes.
would one of those be negative?
A single bond, yep. So what ends up happening, yeah, I'll just draw it right here. When you react with the nitronium ion, your nucleophile can come in and attack that positive nitrogen. One of those bonds breaks. The result is you get oxygen negative, the other one doubly bonded. There's your nucleophile. What charges the nitrogen? Still has 4 bonds, still formally positive. Does that answer that question? Very, very swiftly.
Would those be formal charges?
Yes. Those are formally charged, yeah. Okay. The last slide here is looking at, oh crap, second to last slide. These two species, nitric acid and sulfuric acid, this is the reason why we delayed this lab, was because they're both, you're dealing with these in concentrated form, which means they're a bit dangerous to work with. Please, please, please be super, super careful when working with them. Okay? They will burn you. Okay? You're dealing with them in little dropper solutions, so hopefully it will be fairly difficult to spill anything. But just be careful. Okay? The pKa's aren't going to be as relevant for you, but what will be relevant when we look at the mechanism. Nitric acid and sulfuric acid don't have nitronium. Okay? What has to happen is the nitric acid will react with the sulfuric acid to form an intermediate. That intermediate decomposes to form the nitronium ion, our active electrophile. Okay? Why do I actually particularly like this reaction? Nitric acid would be defined as what kind of a species? An acid. Go figure. Sulfuric acid would be defined as an acid. What did nitric acid act as in this reaction? It acts as a base. It acted as a proton acceptor. So we took a concentrated, strong acid and we made it act as a base. How did we do that? We react it with a stronger acid. Okay? So a lot of the acid-base definitions that we typically work with are pseudo-arbitrary. We can force most acids to act as bases. We can force most bases to act as acids. It just depends on the conditions. When we define our acids and bases, we're typically looking about one central 0 point. What is that 0 point? Water. Okay? That's where we arbitrarily decided to start everything because that water is relatively neutral. That's why we compare back to water. So when we look at an acid, we're saying it's acidic in comparison to water. Okay? When we look at a base, we're saying it's basic in comparison to water. So this reaction is fun just because we can make it do things that are a bit odd. Okay? Questions about any of that? No questions at all, huh? Okay, well, if you don't have any questions,